Let's discuss solve problem 6.6. The question says a boy on a sledge starts from rest and slides down on a snow-covered hill. Together, the boy and the sledge have a mass of 23 kilograms. The hill's slope make an angle of 35 degrees with the horizontal. The surface of the hill is 25 meters long. When the boy and the sledge reach the bottom of the hill, they continue sliding on a horizontal snow-covered film. The coefficient of kinetic friction between the sledge and the snow is 0.100. How far do the boy and the sledge move on the horizontal field before stopping? So this is the figure that describes the problem. Let this be the initial position of the boy, where he is starting to slide from the top of the hill. And since at this point the boy is at rest, his initial velocity will be 0. Then let this be the final position of the boy. And again, at this point, the boy is going to stop. So his final velocity will also be 0. We need to find how far does the boy and the sledge move before they come to a stop. So we need to find this distance d2. To find d2, we are going to use work energy theorem. And since there are friction forces involved, since there are non-conservative forces like the force of friction, we are going to use the generalized form of work energy theorem, which says that work done by the friction force is equal to the change in kinetic energy plus the change in potential energy of the system. So we're going to use this equation to find d2. Let me call this equation 1. To solve this, we will first find what is change in kinetic energy, change in potential energy, and what is the work done by the force of friction. So let's start with kinetic energy. We can write the change in kinetic energy as final kinetic energy minus the initial kinetic energy. Now, kinetic energy is given as half mv squared. So if I have to find k, I write it as half mv squared. We know that initial velocity is 0. That means kinetic energy at this point will also be 0. Final velocity is also 0, so kinetic energy here will be 0. So both initial and final kinetic energies are 0. That gives me the change in kinetic energy to be 0. Then we find what is the potential energy, the change in potential energy of the system, delta U. Delta U, again, I can write as final potential energy minus the initial potential energy. So final potential energy is my potential energy at the bottom here. And since the boy and the sledge are on the ground, they are not raised at a height. The height here is 0. And since they are on the surface, the ground, potential energy at this point will be 0. So my final potential energy is 0. Initial potential energy will be mgh because we are raised at a height h above the ground. We are on the top of a hill and the height of the hill is h. So I write for my change in kinetic energy as, the change in potential energy as final, which is 0 minus mgh. So my change in potential energy will be negative mgh. Then we find the work done by the force of friction. Now there are two cases here for the work done by the force of friction. One when we are going down the hill and the other when we are on the flat surface. In both cases, we have to write down the work done by the force of friction. So we write for them. I will write them separately. For the first case, I will write it as W1. W1 is the region where we move along the distance D1. That will be force of friction 1 times D1. Now, work done by the force of friction we always take as negative because the force of friction goes in direction opposite to the displacement. If my object is moving to the right, the force of friction always acts opposite to it. So work done by the force of friction we also take as negative. So W1 will be negative F1 D1, W2 will be negative F2 D2. And my total work done by the force of friction will be sum of these two works. So minus F1 D1 minus F2 D2. So these are my individual values. And now let us substitute these three equations back to my equation 1. So I will write work done by the force of friction is change in kinetic plus change in potential. Force of work done by the force of friction is this minus F1 D1 minus F2 D2 equals change in kinetic energy is 0, so I'm going to ignore that. I'm not writing 0 here. Delta U is minus mgh. Now we can cancel off the negative sign here because it is present in each term, or you can multiply with minus 1 throughout. And that will remove the negative sign from here. We can write the expression as F1 T1 plus F2 T2 equals mgh. I want to find D2. So we need to rewrite this equation in terms of D2. So the first step to rearranging I will do is I will move this F1 D1 to the other side. And when I do that, my expression becomes F2 D2 equals mgh minus F1 D1. Minus because here the expression was positive. When you move to the other side of the equation, it will become negative. Then we divide by the second force of friction to get D2. F1 D1 F. This is the expression that I can use to calculate what is D2. But I still do not know the value of H and the force of friction. So before I substitute my values here, I need to first find what is H, what is F1, and what is F2. So let us first start with H. H is the height of the slope. And the height of the slope we can find by using trigonometric ratios. The height of the hill. They have given you the length of the hill, D1. I have the value of theta. H is opposite to theta. So I will use trigonometric ratios to find H. Since H is opposite to theta, we will use sine theta. We know that sine theta is opposite side over the hypotenuse. So we will get sine theta as opposite side is H, hypotenuse is D1. So we can rearrange the term and write H as D1 sine theta. I will keep this H here. We will substitute in the expression for D2. Once we have H, let us find the force of friction. By definition, the force of friction is coefficient of friction times the normal force. So in both cases, if I can find the normal force, I will just multiply that normal force with my coefficient of friction to get the force of friction. So in case 1, in order to find the normal force, I first need to split my force due to gravity into its component. So one component goes along the y-axis, The other component goes along the x-axis. X-axis is mg sine theta. Y-axis is mg cosine theta because this is along an inclined plane. My normal force is equal to the y component of gravity, which is mg sine theta. So I can write for the first friction force as mu kf normal, which will be mu k mg cosine theta. Same thing we can do for the second friction force. Again, it will be mu k times f normal. But for the second case, the normal force is equal to mg. We do not split mg here. The normal force and the force due to gravity are equal. So I can write the value of the second friction force as mu k mg. Now I have value of h. I have the force of friction. We will substitute all these three values here in the expression for d. So let's solve for d2. I will get d2 equals mg. H is d1 sine theta minus force of friction 1 is mu k mg cosine theta into d1 divided by force of friction 2 is mu k mg. Mg d1 is common in both the terms on the numerator. Here I have mg d1, here I have mg d1. I can take this out as common. And we can write sine theta minus mu k cosine theta divided by mu k mg. I can cancel off the mg from the top and the bottom. And then we get the final expression for d2 as d1 sine theta minus mu k cosine theta divided by mu k. Now let's substitute. d1 is 25. Sine theta is 35. Mu k is 0.1. And when you solve this, you get your d2 as 122.9 meter, which you can round off to 123 meter. Now you can solve this equation using shift solve at this point over here. If you do not want to rearrange, you can use shift solve at this point. But even when you are using shift solve, you need to first find the value of h, f1, and f2. So you need to do the same thing to find the value of h, f1, and f2. Substitute those values in this equation, and then you can use shift solve to calculate your d2 if you do not wish to rearrange.